What if I ask you this? What is sine of 37 degrees? I don't want it approximately and not from a calculator. So how do you actually compute it? So far, we've built everything from a circle. We started by computing chords by inscribing polygons, finding some seed chord lengths, then using that and Ptolemy's theorem to find chord lengths for 0.5 degree increments. Then we were able to find half chord lengths, what we now call sine, using a recursive rule that gave us sine values for 3.75 degree increments. However, none of these methods gives us an easy way to find the exact sine or cosine value for any random angle. So what do we do? For centuries, the answer was approximation. We build bigger tables, use smaller steps, and get closer and closer. But then, in the 14th century, in southern India, something extraordinary happened. A mathematician named Madhava found a completely different approach. Historians credit him and the Kerala school with discovering infinite series for trigonometric functions, centuries before Newton's rediscoveries in Europe. Instead of stepping around the circle, he asked, can we build sine directly? Think about what sine is doing. For very small angles, the height of the point on the circle is almost exactly the angle itself. Let me show you. Let's take the unit circle, where the radius is 1, and choose a very small angle. But the angle we choose won't be in degrees, it will be in radians. A radian is just the arc length divided by the radius. So if the arc length is equal to the radius, the angle separation in radians is 1. And our radius here is 1, so our arc length is 1 for an angular separation of 1 radian. Since the radius fits, well, 2 pi times into the circumference, there are 2 pi radians in an entire circle. I talk more about radians in part 3a of this series. When we choose a small angle, in this case x radians, where x is really small, the arc length and the height are almost equal, as you can see here. So we can start with something simple. Sine x is approximately equal to x. But there's an important detail here. Today, this only works when x is measured in radians. Madhava did not use radians by name, but he was effectively working with the same idea, measuring angle through the arc of the circle itself. So not radians in the modern formal sense, but yes, in the functional sense. Madhava's series is naturally expressed in terms of arc length and radius, which is exactly the relationship radians formalize. Now, sine x is equal to x is only the beginning. It's close, but obviously not perfect. If I take sine of pi on 2, or 90 degrees, I get exactly 1, but pi divided by 2 is around 1.5. So this assumption starts to break. So Madhava added a correction, then another, and another. Each one fixed the error from the last. This is what he discovered, in modern terms, an infinite series. You first start with x, then subtract a small amount, and add another smaller amount, and subtract another smaller amount, and add and subtract, and so on. If you keep going, you can get as close as you want to the true value of sine for any radian x. This is completely different from everything before. We're no longer using geometry, we're not stepping around a circle, we're building sine using an infinite process. But why does this even work? Why can something as simple as polynomials recreate a curve like sine, an oscillating curve? Because if you zoom in far enough, every curve starts to look simple. Near 0, sine behaves almost exactly like x, hence our assumption sine x is approximately equal to x. And these extra terms gradually correct the shape until the polynomial matches the curve more and more closely. Let me show you. Here we have the graph of sine x, labeled f of x here. And g of x, which I haven't enabled yet, is the infinite series that I showed on the board, but written as a sum. So we have the function y is equal to x when a is 0. And now if I increase a to 1, you can see it suddenly curves and flips. And it seems to be almost the same for up to 1 radian here, before deviating, as you would expect. If I increase a to 2, you can see that the function g of x is very accurate for more than a quarter of the graph, or a quarter of a cycle, sorry. And if I keep increasing, you can see that it keeps hugging it tighter and tighter, and it seems to follow the oscillation of the sine graph. If I zoom in on any point here, you can see that there's no deviation. It seems that we've modeled sine exactly to the point. And that's because the function sine x that's defined in my software here, GeoGebra, is just this function here, g of x, the infinite series. Centuries later, in Europe, mathematicians like James Gregory and Isaac Newton would rediscover and formalize these same kinds of series. And because their work became widely known in Europe, they were often credited with the discovery. But the underlying idea appeared much earlier, with Madhava and the Kerala school. And this is also where the factorials enter the story. Madhava's achievement was discovering the series itself, but later, with Newton and calculus, mathematicians developed a general framework for expansions like this. That framework is what we now call a Taylor series. A Taylor series is a way of rebuilding a function near a point using powers of x. You start with the value of the function, then how fast it changes, then how the rate of change changes, and so on. And when you do that repeatedly, the factorials appear naturally in the denominators. So Madhava found this pattern. Calculus explained why that pattern has exactly this form. Modern Taylor series language, including the factorial denominators, came later with the early modern calculus, rather than from Madhava's original notation. Cosine can be built in a very similar way, like this, and both sine and cos can be written using a summation like this. And tangent is just sine x over cos x, so you just have to simplify this summation. It's nothing new, and all the other reciprocal functions can be represented in a similar way. So, once sine and cosine are known, the rest of trigonometry unfolds from them. From polygons and chords, to recursive tables, to infinite series. We didn't just find sine, we learned how to build it. And every time you type sine of 37 degrees into a calculator, you're not just retrieving a number, you're triggering an infinite process, compressed into an instant. That's it for this video. Thanks for watching, and I'll catch you in the next one.